Hey everyone, it's me, Dr. GB. I just made a video to check in before mini review 3. And first things first, I just want to say I took a look at the quizzes and y'all did super well. And overall, some things that I wanted to quick check in and clarify about that. Overall, again, we all did really well. I didn't see any things that really tweaked my interest. However, there were a few fine points that I wanted to check in about. So first things first about number 3. Number 3 was asking to achieve, it's for that first chemical reaction with methane and water, to achieve a final temperature which is the same as the initial temperature. Does the heat flow into or out of the reaction mixture? So this question was asking, oh hey, okay, it's a delta H, it's positive, so that means heat is going to have to flow in to the reaction to increase the temperature. Now, some of y'all saw this and were like, I see that the wording was a little bit confusing here. Fair enough, I understand. So next time, if I ask you a question about temperature, heat flow, or endothermic and exothermic, I'll make sure to be more precise with my language and try to make it a little bit less confusing. So the other one I saw was for number 8, where y'all had to select the reactions that also represented enthalpies of formation. And so this one was an option. And so at first glance, this one looked like it should be an enthalpy of reaction, because you have methane made from its components, its elemental components, so hydrogen gas and solid carbon. But this would actually not be an enthalpy of formation because the product has 2 moles. And for an enthalpy of formation, that always has to be 1 mole. Now, somebody pointed out that it counted wrong, but I didn't take off points. There's part of me that was kind of like, oh man, but I'm also like, if I don't like taking away points if I had it wrong. So in this particular case, this is just an FYI. This is what it means practically for the reaction to be in terms of 1 mole of product. So the actual enthalpy of formation for this reaction would be down here. So we have to divide everything by 2. So this is why sometimes if you look up standard reactions for enthalpy of formation, why there's halves, even though I've told you many times to avoid putting fractions in your balancing equations, it's because of everything has to be in 1 mole of product. But what I really wanted to actually take some time and go over in detail, because these are the things that I most consistently got questions about, and that is about the enthalpy and thermodynamics of phase changes. All right, so the thermochemistry of phase changes, because this is something that we learned the math behind on like the previous mini review, but we didn't actually talk about thermochemistry and apply it until this section. So even though we didn't explicitly do any phase diagram problems or any cooling and heating diagrams this time, we're still applying and using that knowledge. So I wanted to take a quick minute and give a little refresher. Alrighty, so let's say we're in a situation where we have water. Alrighty, so if we have water, and let's say we start off at a temperature, of minus 20. All right, so if we have water, and so we'll put minus 20, we'll put 0 here and 100 here. All right, and so what's going to happen is we start off with our water in the solid form. Alrighty, so what happens is as we go and as we add heat into our water, our temperature is going to increase until we hit the freezing or melting point. All right. Now, once we take, and so the heat, the energy or the heat associated with this portion is equal to the mass in grams times the CP, which in this case would be the heat capacity of ice, times the change in temperature. So for this, it would be the mass. So it was like 100 grams times ice, which I think is maybe 2.11 grams per degree Celsius, joules per gram degree Celsius, and then delta T would be 20. All right, so that's going to give us our heat. Now, once we've arrived at our temperature, our line flattens out. We have a portion of the curve where our temperature doesn't change with increased heat. And that's because all the heat is going into a phase change. Alrighty, and so what happens to the phase change? So we start off with here, it's solid, and then we go to liquid. I'm going to triangle there. When we start off with solids, all right, solids have the most IMFs, alrighty? Liquids have some IMFs, and then gases have no IMFs, alrighty? So whenever we go through a phase change, what happens during this phase change is we're putting all of our energy into making and breaking bonds, alrighty? So the phase change for here is going to be Q is going to be equal to the moles of our substance that we have times the standard, the enthalpy change, alrighty? So delta H. So in this case, if we're going from solid to liquid, this is going to be the delta H of fusion, alrighty? So fusion is when we go from solid to liquid. Conversely, going the other way, you may also see that referred to as the melting. Conversely, and that is equal to a delta H of fusion, alrighty? Now, the process of freezing, or when we go from liquid to solid, is going to be the same value as the delta H of fusion, but it's going to be the opposite sign, all right? And that's because when we're going from solid to liquid, we are breaking bonds, and that's a positive delta H, so that requires absorbing heat energy to break bonds. Whereas when we're freezing, this is going to be negative, alrighty, because we are making bonds, all right? So when we go from liquid to solid, all right, liquids, again, have some IMFs. They have a fair number of IMFs, but solids have even more. So when we make these new strong bonds, we are going to release energy in the form of heat. Okay, so this portion, so we can calculate, so the delta H of fusion is going to be like a known value that we can look up in the back of the book. And so we can figure out how much energy is either released or absorbed depending on the direction based on the number of moles times that standard value. So the more moles you have, the more heat there's going to be. Okay, so once we get to the end of the road and we've converted, this is the point where we convert solid to liquid, alrighty? So once we get to the end of the road, then we start switching, all right? So once we're all liquid, then we start seeing an increase in temperature again, alrighty? So this is our Q is again equal to M times CP liquid times delta T. So this is CP solid, all right? And this is the CP of liquid for water times delta T, alrighty? So again, if that's 100, we have 4.18 for water, and then our delta T would be 100, alrighty? So all this heat here is going to raising the temperature until we hit 100. So this is the freezing point. This is the normal melting point, or excuse me, boiling point. Alrighty. And so what happens here is this is the point where we start to go from liquid to gas. Alrighty. So at that point, all of our energy is going to go into turning to breaking the intermolecular forces in the liquid and putting them into the gas phase. Alrighty. So again, same thing here where our energy, or our Q, is equal to our number of moles times delta H, but this is the delta H of VAP, or vaporization, alrighty? And this is because evaporation or vaporization is when we go from liquid to gas, alrighty? So, and again, all right, this is positive because we are breaking all of the IMFs, all right? So we're breaking some IMFs from solid to liquid. We're breaking all of the IMFs when we're going from liquid to gas, alrighty? So there we go. Now that's evaporation and vaporization. So then the opposite way would be condensation, alrighty? So condensation is going the other way, and that is from gas to liquid, all right? Again, that's going to be equal to the negative delta H of vaporization, delta H of vaporization, because again, we're going the opposite direction, all right? When we go from gas to liquid, we are forming bonds, alrighty? There we go. Okay. All right, that's all fine, well, and good. So let's try some math here. And I'm going over this because this is something that y'all did. We did individual parts of this together, and y'all did questions on your own in class, but I realized this is a really important thing, but we never actually worked through a multi-phase problem together. And so the question that I'm going to ask you is, I'm literally just going to make up a question on the spot, so this will be a little bit long, so bear with me. You can always put me on like 1.5 speed or whatever. But let's say that we have 100 grams of H2O. Alrighty, and let's say we start off at -5 degrees Celsius. So the question then becomes, okay, how much energy is released when we go to a temperature of 80 degrees Celsius? Okay, alrighty. So first things first, if we know we're going to need our grams, but we also need to look at moles, alrighty? So we need to convert 100 grams times 18 grams of H2O for 1 mole is going to give us, all right, 5.56 moles of water. Alrighty, cool. So we got that many moles of water. Alrighty, so and then our next question is, let's look at our constants. So our heat capacity of solid is 2.11 joules per grams times degrees Celsius, whereas our heat capacity of liquid is equal to 4.18 joules per grams times degrees Celsius. And then our delta H of fusion for water is equal to 6.01 kilojoules per mole. And then our delta H of vaporization is, well, that depends on the temperature, but assuming we're at 100 degrees Celsius, all right, we're at the boiling point, that's 40.7 kilojoules per mole. Now, again, take note, we've got joules in our CP, we got kilojoules in our delta H, so we're going to have to make sure at the end of this we're in the same unit for our energy. And take note that this technically is a lowercase k and this is a capital J. So some of y'all got dinged for units, and I did that back because if we were writing this out by hand, I wouldn't have taken off points for a wrong capitalized letter. But technically, the metric system prefixes are lowercases and our energy units, joules, are capital. Okay, all right, so if I take a look at this, I'm going from what is the delta, what's the change in energy? I guess really the Q here for, if we have, or excuse me, is it the delta? Yeah, the Q4 going from -5 to 80 degrees Celsius. So what we can do then is we have to go, and we have to delta H there. We have to go from, we have to separate this into parts, alrighty? So we're going from -5 to 80 degrees Celsius. So there's a couple of things that are going to happen here. So we have to map that on to our plot up here. Alrighty, so when we start off at -5, we're starting off, maybe over here. So we're going to end up here at 80. But this isn't a linear process. We have to go through 3 distinct state phases. Right? We have our first phase, which is where we're going to add in, when we add in heat, we're going to increase our temperature, okay? So our first step is when we're going to go start off from -5 degrees Celsius and then go up to 0 degrees Celsius. All right? Our second step is our phase change, all right? So we go from solid to liquid. All right, that's our solid to liquid. So we're going to use some energy when we go from solid to liquid. And then finally, our third step is once we've converted all of our solid to liquid, we are like 100% liquid now, okay? What's going to happen is then all of our energy that we put in is going into increasing the temperature. So our second step is when we're going to be going from 0 degrees Celsius up to 80 degrees Celsius. And then once we've figured out the energy change or the enthalpy change associated with every portion, we add them together, and that is our enthalpy. Alrighty, so let's take a look. Okay, so first things first, let's find out what's going on with this step. So we are in the solid form here. We're ice, so we're going to use our CP sub S. So our Q is equal to mass times CP times delta T. So it's going to be equal to 100 grams times 2.11 joules per grams degrees Celsius times our delta T, which is 0 minus -5, which is 5 degrees Celsius. If we go ahead, we do our math here. Again, make sure that you're always going to base your mass unit based off your constant and make sure everything lines up. So we have 100 times 2.11. Make sure your heat capacity matches your phase. Alrighty, so we have 1,055 joules. And again, grams cancel, Celsius cancels, and we are in joules, not kilojoules. Okay, so that's the first step. So that's our Q sub 1, okay? let's look at our second step, all right? That goes from our solid to our liquid. So when we have this is a phase change, all right? And when we're in a phase change, our Q is equal to moles times our delta H. And this is a solid to liquid, so this is our delta H of fusion. All right, so delta H of fusion is 6.01 kilojoules per mole. All right, so we have 5.56 moles times 6.01 kilojoules per mole. All right, there we go. So we go ahead, we do that multiplication. Alrighty, that is 33.42 kilojoules. Alrighty, and again, it's kilojoules because our per mole canceled out. Then finally, we have our last step over here where we're all liquid now. And so our energy is going to go into increasing our temperature until we hit the boiling point, at which point we'll undergo a phase change. But we're not going to get to the boiling point, okay? We're just going to get to 80 degrees Celsius, all right? So we're going to cut off when our water is a liquid. So it's not going to have a chance to be undergoing the evaporation process, alrighty? So when we do this, our Q is equal to M times CP times delta T. Okay, so again, our mass still 100 grams. Our CP now, we're using the water CP, so that's 4.18 joules per grams times degrees Celsius, times our delta T, which is 80 minus 0, which is 80. So we have 100 times 4.18 times 80. Alrighty, and that's going to give us, alrighty. Okay. So that gives us 33,440 joules. Interestingly enough, very close to our previous one. Actually, it's a little creepy. I did not do that intentionally. Alrighty, so we have our energies associated. So our Q total for this transition, so going from minus 5 degrees Celsius up to 80, is going to be equal to the Q1, which is negative 5 to 0, plus our Q2, which is going to be our solid to liquid transition, plus our Q3, which is going to be going from 0 to 80 degrees Celsius. And that will give us, and again, remember, I'm going to say we'll put this in kilojoules. So this would be 1.055 kilojoules. And this would be 33.44 kilojoules. So I just divided those by 1,000 to get those numbers because kilo means 1,000. So that would be 1.055 plus 33.42 plus 33.44. And that gives us 67.92 kilojoules. Again, I'm really trying to be neater here so y'all are getting the right units and not drawing incorrect units based off my work, which looks like the K is the same size as the J, and I'm sorry. So that's why, again, I'm not going to take off for that. Okay. Alrighty, so I hope this video helped you again. I feel like we've done this in terms of fragmentedness. And again, this maps out nicely with our phase diagram. Remember, if we've got our phase diagram, if this is our temperature and this is our pressure, all right, high pressure and low temperature favors solid. High temperature and low pressure favors gas. And then in between is our liquid, alrighty? And this line in the center represents our solid to gas, which is our sublimation, alrighty? Or our delta H of sublimation, alrighty? Solid to liquid, this is our fusion. Alright, so that's our delta H of fusion. Already, and each point is an equilibrium point. And then finally, liquid to gas, that's our evaporation, so that represents our delta H of vaporization. Alrighty, again, these are things that are relevant from the previous section. We implied them, but we never actually directly went over them together. So just wanted to let you know, recap and check in. Everybody have a great, wonderful rest of your weekend, and I'll see y'all in class on Monday. Ciao!